Why don't we go ahead and get started? Today it's my pleasure to welcome Liang from MIT to give this week's colloquium. So Liang is a student of Charlie King at UPenn, back with all of the very exciting work on topological insulators was just beginning. Liang was on many of these papers. And after that, he did a junior fellow at Harvard and later joined the faculty at MIT in 2012. I think he's won a lot of awards.
Okay, great. Thank you, Andy, for inviting me here. It's really a great honor. Today I'm going to talk about some recent works, theoretical and experimental works on electron fractionalization in topological quantum materials. So let me start by thanking. Let me start by thanking all my collaborators. So I got interested in this sort of this direction early on with MIT students, Evelyn Tang, and followed up with work with former postdoc Jan van der Bos and then Zhen Bi. And the recent works that I'm going to talk about started in collaboration with Tristan Devacourt, and was a postdoc at that time, and recently moved to Stanford University, joined as a faculty member there, as well as my former student, Valentin Krepel, who is now at the Flatiron Institute, together with Yang Zhang, who is now on the faculty of the University of Tennessee. And then, starting from 2023, we have been working a lot with my group on this topic. My student Aidan Reddy and Nishaga Paul played a big role. And some of the works involve postdocs Hart Goldman, who is now about to join the faculty of the University of Minnesota. Xueyang Song is joining the Hong Kong University of Science and Technology. And Ahmed is a new postdoc that arrived recently, and also have benefited a lot from the collaborators outside MIT. And finally, I want to thank the collaboration with experimentalists, Xiaodong Xu at the University of Washington, Seattle, Long Ju, my colleague at MIT, as well as Ben Feldman from Stanford. So as we know that solids exhibit a wide range of phenomena that collective phenomena that are governed ultimately by the fundamental laws of quantum mechanics on the atomic scale. And for example, the ordering of electron spin in the same direction give rise to ferromagnetizm, condensation of electron pairs that leads to superconductivity. And one of the important concepts, to understand the behavior of quantum phases of matter, an important concept is quasiparticle. These are particle-like excitations above the zero temperature ground state. And the simplest example is consider semiconductors, and with an energy gap separating the filled valence bands and the empty conduction bands. In this case, because of the Pauli exclusion principle, to add electron, an added electron has to be living at the bottom of the conduction band, and a removed electron or a hole has to live near the top of the valence bands. So these are electron and hole quasiparticles. They carry opposite charge, minus E and plus E, and they really determine the electrical properties of semiconductors at temperatures below the gap. So basically, these quasiparticles, they move freely as if it were in vacuum without bumping into any of the nuclei. Okay? So that's why this concept of quasiparticle is so useful. The physics of semiconductors is faithfully captured by a gas of electrons and holes. So in this case, the these quasiparticles are different from the original electron. For example, they can have different masses, and the holes can carry a positive charge, but still not too far. Okay, that sort of in essential ways similar to the bare electron. And combining electron holes, we can create composite quasiparticles. For example, a bound state of electron hole is an exton, and they determine optical properties of semiconductors. In a magnet, a spin flip is an itinerant particle called a magnon, and in a superconductor, 2 electrons pair into a charge 2e boson. So from this perspective, it is somewhat counterintuitive, but remarkably, the solids can also, electronic quantum states of matter can also have elementary excitations that are actually fractional, meaning that quasiparticles can carry a fractional charge in a system made of electrons. Okay, can carry, for example, 1/3 of electron charge. So this was first realized, discovered in the context of the fractional quantum Hall states. That was experimentally discovered in the 1980s, and this has remained a subject of intensive research into this day. And here, this fractionalization really occurs in semiconductor heterostructures under a very strong magnetic field that place these electrons into the so-called Landau levels. So it's a universal properties of the Landau level. Okay, and so one may ask, can this phenomenon also occur in the absence of magnetic field due to the intrinsic material properties? And this is something that, sorry for, I don't know why it didn't show up properly. So this question has sort of intrigued physicists for a long time, and finally, last year, we have seen 2 experiments on 2 different platforms, and these are basically moire materials with topological bands that I'll explain, and these show fractionalized phases at a 0 magnetic field. Okay, so the idea is that the physics of Landau level is now replaced by that of the topological band. So our review, sort of, I was going to look back at the path it took for the community to get here. So what we have learned, what worked and what didn't work, or at least hasn't worked so far. And more importantly, I'm going to discuss sort of the new physics that topological band is going to bring us. Okay, so first thing first, so the to explain the quantum Hall effect, let's start with the classical Hall effect that was known since the late 19th century. So as we pass a current through a conductor in the presence of magnetic field, a transverse voltage develops in the direction that's perpendicular to both the current and the magnetic field. And so this phenomenon can be understood very simply by the fact that in the magnetic field, when you have a moving charge, it experiences a Lorentz force. So the transverse voltage introduces a transverse electric field that counterbalances the Lorentz force. And this leads to a very simple relation that the Hall conductivity is basically set by the electron density divided by the magnetic field, or the Hall resistivity is simply linear proportional to the magnetic field. This is indeed the classical Hall effect. However, in the study of this Hall effect in semiconductor heterostructures, where electrons are confined to the surface layers of semiconductors, it was found in the 1980s that the Hall effect actually the Hall conductivity can be quantized into some multiple of E squared over H. E is electron charge, H is a Planck constant. And the first, it was found that these quantized Hall conductivity occurs with an integer coefficient, the so-called integer quantum Hall effect. And shortly afterwards, it was found that there's many quantized Hall states with fractional coefficients P over Q. So this is the beginning of the physics of electron fractionalization in condensed matter physics. So, so very roughly speaking, in a high magnetic field, the electron turn into these cyclotron orbits, and each orbital takes up an area that corresponds to 1 flux quanta. So one can define the Landau level fitting factor, which is the number of electrons divided by the number of total number of flux quanta, which is basically the electron density divided by the magnetic field. And the Landau levels are separated by energy gaps, the cyclotron gap. So when an integer number of lambda levels are complete filled, or in other words, when the filling factor is an integer, then we can get incompressible states with a single particle gap. And or at a fractional filling of a lambda level, in particular the lowest lambda level, then strong interaction effects can lift the degeneracy within the partially filled lambda level, and this can drive the system into a collective many-body states, and that, again, give rise to a many-body energy gap. So regardless of the origin of the gap, whenever a gap develops in the energy spectrum, the Hall connectivity will be quantized in the case of the lambda levels. Basically, if we look at the classical formula for the Hall connectivity and express the density in terms of filling factor, we see that it's simply just the filling factor times E squared by H. So at the integer filling of lambda levels, we get the integer quantized Hall connectivity. At fractional fillings, such as 1/3, we get fractionally quantized Hall connectivity. Okay, so how is this related to fractionalization? Well, as shown by Laughlin from early on, that whenever the Hall connectivity is fractionally quantized, it implies the presence of fractional charge, P over Q times the electron charge in the system. And this Laughlin argument goes as follows. Imagine inserting a flux quanta through a single solenoid, for example, at the center of a quantum Hall disk. Then the time-dependent flux induces electric field in the circumferential direction. And then because of the Hall effect, it drives a current in the radial direction. So when the flux changes from 0 to H over E, the integrated current over the whole circumferential of the whole circumference is the following. It's basically given by sigma xy times the change of the flux. Okay, so when the flux changes by a flux quanta, we get an accumulated charge at the origin, which is sigma xy times H over E. And when there's one flux quantum, we know can be gauged away. So this means that the system must support a fractional charge that is given by the Hall connectivity. Okay, and so this So for a quick review of the quantum Hall physics, I just want to highlight that this quantum Hall effect is really a universal property of lambda levels in the high magnetic field. It occurs in many semiconductor heterostructures originally discovered in silicon and later gallium arsenic, zinc oxide, etc. And more recently, with the discovery of two-dimensional materials such as graphene, the quantum Hall effect was observed there, and that led to the first understanding of the electronic structure of graphene. So these are importance of the quantum Hall effect was recognized by many Nobel Prize in the past. So what about the zero field? So can we get the quantized Hall effect without magnetic field? Well, it's also known since the late 19th century. There's something called anomalous Hall effect, which occurs in ferromagnets. And here, even at zero external magnetic field, there could be a finite sigma xy that is generally unquantized. And the macroscopic origin is the following. If we think about the electrons in a solid, its electron wave packet actually has a center of mass, but it also has an internal distribution within different parts of the unit cell. Okay, so in the presence of electric field, the center of mass of the wave packet moves according to this simple Newton's law. Electron wave packet is accelerated by both electric field and by the magnetic field if it's present. But then, as electron's momentum is accelerated, the electron wave packet also redistributes within the unit cell because the electron wave function, intra-unit cell wave function, depends on the momentum. As momentum accelerates, electron redistributes within the unit cell. This leads to an additional current flow. And interestingly, this current flow, this additional anomalous flow, is always perpendicular to the rate of change of the momentum. And that's why it leads to a transverse anomalous velocity. Okay? And this anomalous velocity is proportional to the electric field, which accelerates the momentum, and is proportional to this quantity called the barrier curvature. So this barrier curvature is entirely a property of electron wave function in momentum space. Okay, and with this anomalous velocity present, then electric field will accelerate the electron in the same longitudinal direction, but it also gives rise to a transverse velocity that's linearly proportional to the electric field. This means that there will be a Hall effect, and in the absence of magnetic field. In the extreme case, if we take a non-interacting system with a complete field bands, then the Hall conductivity is simply given by the integral of barrier curvature over all occupied states, and in this case, the integral extends to the entire Brillouin zone. And this quantity actually turned out to be a quantized topological invariant called a Chen number, and this explains that the Hall conductance must be quantized into some integer multiple of e squared over h. Okay. And this relation between barrier curvature and the Chen number is somewhat analogous to the relation between the geometric curvature and the genus, which is a topological invariant of manifolds. And the Landau levels, each Landau level carries a Chen number of 1, but theorists such as Duncan Haldane from early on contemplated that perhaps one can get the same quantized Hall effect just purely from band structures in the absence of any external magnetic field. You take a band structure, for example, models on the Huntington lattice with appropriate terms, one can actually create a valence bands that carries Chen number 1, just like that of Landau level. And in this case, in principle, one can get quantized Hall conductance. However, one important open question from early on is that in order to create such an effect at the zero magnetic field, the system must break time rules of symmetry in some way. And this requires basically a magnetic order. So that's why the anomalous Hall effect is observed in magnetic materials. And most of the ferromagnets are metals, while here, in order to achieve a quantized anomalous Hall effect, it requires a ferromagnetic insulator with an energy gap. And it requires that the occupied bands carry a finite Chen number. So one really needs a synergy between magnetism and topology. So after a long time, then only after the discovery of topological insulators, people realized there's a path to create these quantum anomalous Hall states. So bismuth telluride is a three-dimensional topological insulator, and it has surface states which are gapless Dirac cones with the Kramer's degeneracy at the Dirac points. And in this case, if one introduce a ferromagnetic order on the surface, this will break time rule symmetry, and it will generate a mass term at the Dirac point. And with a massive Dirac fermion, there's a barrier curvature that leads to a quantized Hall effect, which is 1/2. And if we combine the top and the bottom surfaces together, and if the magnetization on the top and bottom surface are in the same direction, then the Hall conductivity add up 1/2 plus 1/2. This will lead to a quantized integer quantum Hall effect. And one way to achieve this is to use magnetic doped topological insulator films. So basically bringing magnetism and topological bands together. And this was experimentally realized in 2013, more than 10 years ago, in this chromium-doped bismuth telluride film. Here, as you see, that the Hall resistance is quantized even at the zero field when the gate voltage tunes the Fermi level inside the gap at the Dirac point, introduced by ferromagnetism. And so this is sort of the first realization of the quantized Hall effect at zero magnetic field, and it brings the physics of quantum Hall effect, so liberated it from Landau levels into actually quantum materials, and was highlighted in the Nobel Prize in 2016. So now comparing these two platforms, there's similarities and differences. So in both cases, we can get a band with a Chen number 1, either Landau level or from intrinsic time rule symmetry breaking. But in the case of magnetic doped topological insulator, these energy bands are not at all flat, right? The bands actually connect all the way into the bulk, so with a bandwidth on the order of at least 100 millielectron volt, while in the case of the Landau levels is completely flat. Also, in Landau levels, the barrier curvature is uniform, while in the case of these term bands in magnetic topological insulators, the barrier curvature is all concentrated near the direct point. So if we think about the possibility of fractional quantum Hall states, then the case of the magnetic TI is unlikely to work. So it's not possible to really gate the system to partially occupy this dispersive term band, and it's unrealistic to expect interactions can overcome the large band widths to create interesting states. Okay, so one need to go look for elsewhere. So this brings me to the main subject of this talk, is how people as a community has been looking for bands that are both flat and topologically non-trivial, and how the platform supporting such topological flat band may provide an opportunity to realize this fractional quantum Hall effect at zero field. Okay, so this is a challenging task, right? It's like looking for a needle in a haystack. So there are all kinds of materials in nature. So what we look for, right? So the moral of the story I'm going to tell you is really this: if you cannot find one, make one. So it really by creating artificial materials, one can satisfy all the requirements, topological and flat. So so for me, I've got interested in this subject inspired by the early theoretical and experimental work in graphene in the presence of a strain. Okay, so we all know that the graphene has direct points. Now, under a strain, theory predicts that these direct points will shift under a uniform strain. So this means that strain acts in a similar way as a vector potential, which displays momentum in k-space. And this then further implies that if I have a spatially non-uniform strain, the strain gradient will then act as a magnetic field. The gradient of vector potential is a magnetic field. But of course, strain preserves time-Russell symmetry. So it's in this sense, the strain acts as a magnetic field in each valley, but with opposite sign. So basically, a strain gradient creates opposite magnetic field for the two direct points in opposite valleys. And this experiment from Micromics group in 2010 showed that if you look at a nanobubble in graphene, where there's a highly non-uniform strain locally around, we do see that the energy spectrum goes exactly as you expect for Landau levels. Okay, Landau levels. So there are peaks in the denser states, as you expect from the flat Landau levels. Now, however, so at that point, there are a lot of interest theoretically of whether this kind of a strain can be used to produce quantum Hall and fractional quantum Hall states in graphene. Now, in the case of a nanobubble, the strain is very strong, but it's highly localized. So one may think that natural idea is to create a strain superlattice, a periodic pattern of strains. Here, actually, one immediately see there's a big problem. And so we know that if you look at if you have a periodic pattern of strain, this creates a periodic vector potential, but then the integral of the magnetic field over all space then would be the integral of the gradient of the strain, okay? And in this case, it would go to zero if the strain field is periodic. So this means that the pseudomagnetic field in the strain superlattice is not only non-uniform, it actually is spatial alternating, and it averages to zero. This is very different from the case of a real magnetic field that creates Landau levels. So indeed, we did some numerical study of this problem of one-dimensional periodic strain graphene. We see that we do not get isolated Landau levels at all. Instead, we see that we get many minibands, but these bands are flat at the direct point, but they still connect to high energy. So these are partially flat bands. Nonetheless, when the direct point turn into a flat segment, electron interaction effect can be strongly enhanced. So we show that interaction can actually induce spontaneous orbital ferromagnetism, open up a gap at the direct point. In other words, it generates, interaction can in principle generate a so-called Haldane gap, and it can lead to an integer quantum Hall effect. But because these bands are not completely flat and not isolated, it's really not possible to create fractional quantum Hall states at partial filling of this. Okay. So another idea that has, again, been around for quite some time is about using magnetic skyrmion superlattices. Okay. So skyrmions are topological textures of electron spins in real space, and there are a number of magnetic skyrmion materials where skyrmions form a nearly periodic array. And again, it's known that when the spins are non-coplanar, it creates an effective magnetic field that is given by the spin chirality. So the basic idea is that when electrons move in the spin texture, the electron spin is locally aligned with the spin texture. So if you go around a path, a closed path in real space, the spin of the electron would also move around in the block sphere. And this creates a Barry phase in the same way as the Hadron bomb phase electron picks up going around the circle in the real magnetic field. So the analogy between the Barry phase and the Hadron bomb phase implies the the magnetic skyrmion superlattice creates an emergent magnetic field. And this leads to the Hall effect, again, a zero external field, and that's called the topological Hall effect. So, so in this case, then one might expect the possibility, right? One may speculate the possibility that this topological Hall effect can become quantized. But the problem is, in order to create this quantization condition, one really need to have a system of low densities. One need, roughly speaking, just one or a few electrons per skyrmion. So the filling factor is really the carrier density divided by the skyrmion density. So the condition for realizing quantum Hall effect is a low density skyrmion material, and that has been a challenge. So most of the skyrmion materials are metals with very high densities. So, so in 2021, together with my student and postdoc, we explored the possibility of using a semiconductor layer in proximity with a magnetic layer to create this favorable condition. So in the semiconductor, it's basically described by a simple electron gas with a kinetic energy p squared over 2m. And the magnetic layer introduces this proximity exchange field that couples to the electron spin in the semiconductor layer. And in this case, for example, if you take MOS2, it's a two-dimensional semiconductor in proximity with this chromium-bromium, which is a magnet. Our DFT calculation found that there's a very large exchange splitting on the order of 14 milletron volt. And these magnets also can develop skyrmion textures, especially take the so-called twisted magnet. And so we played around, take the sort of most common profile for the skyrmion lattice, and we find that very generally we get these mini bands that are very flat, and all of these bands have a Chen number 1, very similar to Landau level. Okay, so this in principle could work. Now, but we all know that in terms of the mini bands, the best platform is actually the moire superlattice. Okay, so it was predicted in 2012 by Alan MacDonald that you take, for example, 2 layers of graphene and twist it with a small angle, you create this long wavelength moire pattern. And my colleague Pablo's group discovered superconductivity and other interesting phenomena in this kind of magic angle twisted bilayer graphene. But then very quickly, the experiments at Stanford and UC Santa Barbara showed that when this magic angle graphene is further aligned with the boron nitride, the system actually develops surprisingly orbital magnetism. So it's a system made of carbon atoms without magnetic elements, but it becomes a ferromagnetic, and it leads to the enormous Hall effect, which is very large, and it's quantized in some devices. And this again created a hope that this could be further lead to the observation of a fractional quantum Hall effect. Okay, so again, here the idea is that even though the system is nominally time-Rousseau invariant, within each valley there can be Chen bands, which can be moire bands, which carry Chen number equal and opposite at the 2 valleys. So the whole system consists of time-Rousseau pairs of these moire Chen bands. And also there are theoretical proposals showing that if these system is spontaneously spin and valley polarized, one might be able to get the fractional quantum Hall effect, zero field. And the best evidence so far is from the Harvard group from 3 years ago. And they observed indeed a fractional quantum Hall effect, but still requires a magnetic field of more than 6 Tesla. While at small and zero field, the Hall conductance is 0. Okay. So this led us to look for other platforms. So in 2021, the 2 theoretical groups, one is by Kai Sun and Shizhen Lin, and then my group, we both identified these twisted semiconductor bilayers as a promising platform for both integer and fractional quantum Hall effects. And these semiconductors include, for example, MOTE2 or WSE2. Okay, both of them are transition metal dichalcogenides, and the physics is pretty much similar. And in addition to these integer and fractional states, these systems also host a wide variety of interaction-induced phases, including Mauldin suitors, charge-dense waves, and other topological phases, including quantum spin Hall states. So this is what I'll tell you about. And so both Kai Sun's theory and our theory, we rely heavily on the key work by Alan MacDonald, who first pointed out that these twisted semiconductors can have topological bands. So in these systems, electron spin is locked to the valley, so due to the strong atomic spin-orbit coupling, and these 2 valleys are far apart in momentum space, so we can, at the single particle level, we can treat the spin up and spin down electrons separately. And Alan pointed out that if you take the twisted semiconductor, the continuum model for the band structure actually is very similar to that of a spin skyrmion lattice that I showed you earlier. And here, what replaces the role of the spin is a layer degrees of freedom. Okay, the top and bottom layer can be regarded as a pseudo spin, sigma z equal up and down, plus and minus. And the potential difference between the 2 layers acts as a Zeeman field in the z direction, while the interlayer tunneling, which is off diagonal, it acts as a pseudo spin Zeeman field in the xy plane. Okay, and because of the moire structure, both the z component and y component of the Zeeman field are spatially varying with the periodicity of the moire superlattice. And in particular, because the moire bands come from the valley K and K prime point in the Brillouin zone, the interlayer tunneling amplitude is actually complex. There's a tunneling form factor, e to the I k dot a, where a is the atomic scale lattice constant. And this guarantees that this Hamiltonian is complex valued, and it supports a non-coplanar pseudo-spin texture. So the net result is that Alan predicted that this system should have time reverse pairs of Chen bands with a spin up electron in K valley, spin down electron in K prime valley. So they together form a pair. Okay. So again, the system at the single particle level preserves time reversal symmetry. So so we look at the possibility of how the system may spontaneously break time reversal symmetry and leads to the quantum Hall effect. So this is a plot of the band structure as a function of twist angles. At the large twist angle, even though the bands are still topological, the band width is very large. So this is unfavorable for ferromagnetism. Okay, so spontaneous polarizing all electrons into one spin, one valley simply costs too much kinetic energy. It's unfavorable. On the other hand, we showed that when we go to smaller twist angles, the bands generally become quite flat, and this actually creates a condition that's favorable for strong interaction effects. And in particular, there's a magic angle, which is about 1.4 degrees for twisted WSE2, where the lowest band for holes is most flat, and the barrier curvature is most uniform, so it strongly resembles the Landau level. The band width is obviously tunable by the twist angle. Also, the band topology can be tuned by an outer plane electric field. So this system, we suggested, is a very rich platform. And so we further did the many-body calculations, and at a small twist angle, and at a small electric field, we find that the ground state is fully spin polarized at a whole range of filling factors, not only at integer filling, but also at the partial filling. And because of the fully spin SD polarization, it means that in the ground state, electrons only occupy Chen bands of one spin species. So this creates, this strongly mimics partially filled Landau level. Okay. Moreover, if we are at the filling factor 1, then the complete filling of spin polarized Chen bands will lead to a quantum Nernst Hall effect. And at a partial filling, then the system resembles of a fractional field Landau level. So this naturally raises the question: can we get the fractional quantum Hall states? And in the case of Landau levels, whenever you have a fractional filling, whenever an energy gap develops, the Hall conductance will be quantized into the filling factor times E squared of H. But more generally, what happens? This was pointed out actually by Chen Yu back in 1984. That very generally, the fractionally quantized Hall conductivity is actually a topological invariant of the many-body ground states. It's called the many-body Chen number. So basically, in this case, the system can have degenerate ground states, and the ground state manifold together share an integer Chen number, which means that each particular ground state carries a fractional Chen number. That's called the many-body Chen number. And also early on, that theorists showed that in toy models for these kind of flat Chen bands at fractional filling, the system can support these fractional quantum Hall ground states. These are called the fractional Chern insulators. So now, so in the case of these twisted semiconductors, at near the magic angle, let's say 1.4 degree, we see there's a very flat bands. And my student Valentin Kreppel studied what happens at the fractional filling of these Chen bands. So we find various types of ground states. At some special fillings, we get a fractional Chern insulator. But then there's also strong competition with topologically trivial states. That's a charge density wave. Also, at the generic filling factors, we find that the ground state can be a metal with an unquantized Hall effect. So we call it a Nernst Hall metal. Okay, so the phase diagram is quite rich. And the one way to nail down these fractional states in numerics is we look at the ground state degeneracy and how these ground states evolve as we twist the boundary condition. And we see here that the 3 degenerate ground states, they all permute as we change the twist boundary condition. And this is the characteristic signature of fractional Chern insulators. Okay. The Ben Feldman's group at Stanford University, they actually carry out experiments on twisted WSE2. And this is a plot of the so-called compressibility as a function of magnetic field and the filling factor. Basically, the d mu dn, the change of chemical with respect to the density, this is actually equal to the ground state Chen number. Or actually, dn d mu is equal to the Chen number. So basically, what I want to call attention to is basically these high intensity lines. These indicate incompressible states, and the slope of these lines is the Chen number. So at 1.2 degree, very close to our predicted magic angle, it was found that the quantum Hall states appear down to 0 magnetic field at filling factor 1, and this is exactly what we expect from complete filling of a Chen band of a spin polarized electrons. Okay. Now, in this system, unfortunately, so far we haven't found the fractional states yet because the twist angle is very small, the disorder effect is very strong. But in twisted MOT2, the Xiaodong Xu's group discovered both integer and fractional quantum Nernst Hall states. Okay, and moreover, the fractional states appear not just at one filling factor, but at least 2 filling factor, both 2/3 and 3/5. And this is the plot of the Hall conductance Rxy and Rxx. Each plateau of the Rxy is accompanied by a minimum in Rxx. And all this occurs at 0 magnetic field. And also, ferromagnetism was observed in a wide range of filling factors. Okay. So then when it rains in that pause, my colleague Liang also discovered last summer a completely new system, unexpectedly, also shows the fractional quantum Landau Hall effect. And this is a multi-layer graphene aligned with a boron nitride substrate. And here you can see the many RXY plateaus and the whole sequence of fractional quantum Landau Hall states. So, so to summarize, so far I've shown that basically with the advent of topological and moire materials, it really enabled the observation of intergent fractional quantum Hall states, a zero field, and these occur due to the combination of spontaneous time reversal symmetry and topological bands. So I've shown you that under good conditions, topological bands can show a lot of similarity with Landau levels. But now let me use the last few minutes to tell you a bit about the differences. So what kind of new aspects does topological bands bring in addition to fractional Hall effect at zero field? So I'm going to mostly focus on the twisted semiconductors, which is much better understood theoretically at this point. So, we show that we found that in twisted MOT2, at a very small magic angle, about 2 degrees, the phase diagram as a function of filling factor strongly resembles that of the lowest Landau level. There's a whole set of fractional states at filling factors both above and below 1/2. Okay. On the other hand, at the larger angles, which are currently the devices currently studied devices fall into the second category. Our numerical calculation showed that there's a strong asymmetry above and below half filling. So above half filling, we see several fractional quantum Hall states, including 2/3 and 3/5. But below half filling, in particular at 1/3 filling, we see a different state, which is a charge density wave. Okay, this is something that's different from that of the Landau level. In fact, the most famous fractional quantum Hall states is the Laughing state occurs exactly at 1/3 filling of that of lowest Landau level. Here, 1/3 is a charge density wave, 2/3 is a fractional quantum Hall. That's our prediction. And also we find that between 2/3 and filling factor 1, the system actually becomes simply a metal with a well-defined Fermi surface. Again, that's something different from the Landau level case. So, so recently, the Cornell group actually again measured the compressibility of twisted MOT2, and indeed they found that at filling factor 1 and 2/3, system supports intergent fractional quantum Landau Hall states. You see these lines have finite slopes equal to 1 and 2/3, but at 1/3 filling, you see there's a vertical line in the dn d mu, which says the Chen number is 0. So this is actually consistent with charge density wave. And transport experiments from the Seattle group further showed that at the filling factor between 2/3 and 1, the RXY quickly drops to a value that's below sigma xx. So meaning that in this range of filling factors, the whole angle is small. So that's exactly what we expect for a ferromagnetic Fermi liquid, the anomalous Hall metal. And also, another interesting feature, you notice that in addition to these incompressible states, unlike the 2/3 and 3/5 states, at half filling, the system does not show any incompressible feature. It seems to be a compressible state where RXY changes smoothly, and there's no dip in RXX. But at half filling, the value of RXY is very large. It's much larger than RXX. So this, so what is the nature of the Chen band at half filling? So we know that in the case of Landau levels, the half filled lowest Landau level is a composite Fermi liquid. That the low energy degrees of freedom are not electrons, but electrons bound with 2 quanta of statistical flux. Okay, basically attaching 2 flux to an electron leads to this object called composite fermion. So the composite fermion actually move in the effective magnetic field, that is external field minus the statistical flux. And at half filling, the external field and the statistical field, they cancel each other, so composite fermions live effectively in a zero magnetic field, and that leads to a Fermi liquid of composite fermions, known as composite Fermi liquids. Okay. Now, our calculation showed that indeed in twisted MOT2, when the Chen band is narrow, when the bandwidth is small compared to international energy scale, we find a similar composite from liquid states. And on the other hand, at the larger twist angles, when the bands become dispersive, the ground state simply become a Fermi-liquid with a well-defined Fermi surface. So one way to tell the difference is to look at the photon emission experiments that probes the electron spectral function. Okay, this is something not possible to do even in Landau levels because of the strong magnetic field. But with these zero field fractional states, one can apply this powerful technology of the photon emission to study the electronic spectral function. So the prediction is that in the Fermi-liquid state, one should see a well-defined Fermi surface. On the other hand, in composite Fermi-liquid states, despite the system is compressible, despite it conducts electricity, the spectral function should be smooth and it should be relatively uniform in K-space. That's a sharp distinction. We also found that in the clean limit, these two types of states are sharply distinguished by the Joule weight. So in the Fermi-liquid, there's a finite Joule weight, meaning that if you look at optical conductivity, there's a delta function peak at the zero frequency in the clean limit. On the other hand, in the composite Fermi-liquid state, the Joule weight vanishes. There's no delta function peak. Okay, so as we tune the bandwidth, the system can undergo a transition from a composite Fermi-liquid state to a Fermi-liquid state. So the optical conductivity is another way to distinguish these two phases. So this field is now developing really rapidly. So so far, everything I've told you is what occurs at fitting factors less than 1 when the spin polarized Chen band is partially filled. But when we go to higher fitting factors, new phenomena can occur that involves both spin states. Okay, because the two spin states, and the two which occur in different values, they have opposite number related by time rule symmetry. Okay, one can think of it as the K value is being similar to a Landau level with positive magnetic field. The K prime value is similar to a Landau level in opposite magnetic field. So when both values are involved, then the system has no analog at all with quantum Hall systems in Landau levels. Okay, and the recent experiments from Cornell group show that the system actually may support some quantum spin Hall states that are fractional. Okay, that are fractional, and this may occur at fitting factor 3. And theorists have proposed all kinds of interesting scenarios. For example, this work showed that if you have a half-filled Chen bands related by time rules of symmetry, and then this can lead to a time rules invariant fractional topological insulator with as many as 32 types of fractional quasiparticles. And another work proposed a different kind of states, and all these are still being sorted out. So, and so let me just wrap up. That fractionalization is basically interesting and important theme in condensed matter physics. And I've so far discussed fractional charge, but it's also known that these fractional charges also carry fractional statistics. Exchanging these two fractional quasiparticles, it gives you a phase factor that's neither plus or minus 1, different from bosons or fermions. They can have statistics intermediate between the two. And even more exotic possibility is so-called non-abelian anyons. And in this case, exchanging the position of two fractional quasiparticles can actually change the state of the system. And this has been proposed to be useful for topological quantum computing. Information can be encoded in these distinct ground states, and logical operation can be performed by braiding these quasiparticles in a protected way. And the physics of fractionalization is deeply tied with the mathematics of topological quantum field theory. And in these field theories, the word lines of Wilson lines corresponds to the space-time trajectory of these fractional quasiparticles. And the braiding is described by the braid group of these Wilson lines. And also there are more exotic generalizations of fractional charges in higher dimensions, including fractons, the fractional quasiparticles. Also, the physics of fractionalization is also related to the physics of quantum error correction, and that's for topological quantum computing. And in addition to the Chen bands, there are many other platforms that are proposed to host fractional charges, in particular quantum spin liquids, as well as AMO systems. And there are many experts in the audience in this department are working on many aspects of fractionalization. So with that, I'm going to stop here. So basically, after 40 years, we have broken the monopoly of the Landau level physics. The fractionalization now can appear in more settings, and they bring some new physics. There are many paths to fractionalized phases. Thank you.
So we should have time for some questions.
So why is it that right, the basic kinetic energy dominates, right? In the case when the bandwidth is very large, then the kinetic energy dominates over interaction. So in that case, we expect just a simple Fermi liquid. When it's complete field, you get an integer quantum Hall effect. Right, that's no problem. But a fractional fitting and system, yes, question.
Yeah. So what is a good motivation to look for new platforms to see fractional flow physics without going beyond conventional fractional flow physics? You could say, oh, well, we have fractional flow effect in semiconductor structures, so I would look at these two platforms. What is a good answer?
Yeah, so this is an excellent question. Yeah, so actually, one is about energy scales, which I didn't have time to talk about today, but on Friday I'll say more about that. It's related to energy gap, right? In the case of the Landau levels, the energy gap is very small. It's basically, even the Landau level gap is already small to begin with, and the gap at the fractional fitting is even smaller. But in these twisted semiconductors, for example, even twisted MOT2, at the fitting factor 1, the integer quantum anomalous Hall states has an energy gap of almost 10 millielectron volt. Okay, and that's very large. It corresponds to 100 Kelvin. And indeed, quantization was observed up to 12 Kelvin. That's the largest quantum anomalous Hall operation temperature so far at zero field. So if you go to other platforms, imagine we can find this fractional Hall states, right, in a system with a smaller unit cell. In other words, at a larger electron density, then the whole energy scale can go up. Okay, so maybe one can create even ideally room temperature, right? Fractional states. That will be a dream. That's one reason. And the other thing that I want to highlight is that these topological bands not only brings this fractionalization, fractional Hall physics. That's so far the most explored so far. But it could also be an interesting platform for other phases, including, for example, chiral spin liquids. Right? Yeah, and also briefly mentioned towards the end, there are these time Rosen invariant phases, fractional phases, the fractional topological inserts, for example. Yeah, so these are pretty much they are pretty much under exploration right now. Yeah, so it's a big open question. Yeah. So basically, I want to say that when a band becomes topological, right? In strong interaction effects in a partially filled topological band, there's many interesting possibilities that I think the community hasn't thought of as much before, compared to just strong interaction in a narrow non-topological band, right? So in the non-topological band, there's a lot of physics about Hubbard model, right, at half filling, et cetera, But what happens at this half filling of a topological band, right? These are all much less explored.
Okay, Margaret.
So what, I guess if you have this topological band, no way, so you're asking, can we determine? Right. So certainly, with exact dimension method, numerical methods, we can. And actually, there's also a lot of, by this point, there are a lot of more understanding. So, for example, yeah, it's a good question. I didn't have time to go through this. In the case of the, so you may ask, what is the origin of this, difference between 1/3 and 2/3 fitting? So why is it the 1/3 fitting in the ground state is a charge density wave, but the 2/3 fitting is a fractional Hall states? Right. The answer is the following. So the Chen band in this system, you can map it into lambda level with a periodic potential. Okay, because the continuum model in this system is that of a skyrmion lattice. One can actually carry out in an essentially exact way, a mapping between the skyrmion lattice problem and the problem of a magnetic field. There is a difference that the magnetic field is not completely uniform, it's spatially varying. And second, in addition to the effective magnetic field, there appears a periodic potential. So that periodic potential in twisted MOT, that effective periodic potential for twisted MOT2, it has triangular lattice symmetry. It has a minimum that form a triangle lattice. So if you have 1/3 fitting, it's easy to pin the Wigner crystal at this external potential minima. So that's why the CW state gets strongly favored. On the other hand, at 2/3 fitting, the Wigner crystal state at 2/3 fitting would form a honeycomb lattice, which is actually at the maximum of this potential landscape. So that's strongly unfavored. So that's why we get the fractional quantum Hall states instead. Yeah, fractional quantum Hall states. So more and more we are starting to understand better the physics of these Chen bands. Yeah.
Okay, maybe I have a question on the next slide.
Yeah.
I think. Maybe it's very simple, but.
This one. Yeah.
Yeah. So, what's the mechanism in this Buddha weight?
Yeah. That's actually a great question. Yeah. So, right. So, the one way to think about this is that, So the one way to think about it is think about the form of the conductivity tensor in the composite fermi liquid phase. So when you attach the flux to the composite fermion, right? It's basically the electrical conductivity of the system. You can deduce its electrical conductivity, its resistivity, from the sum of the resistive composite fermions and that resistivity of the vortices. Right. So you can think of the flux attachments attaching vortices to the electron, convert them into composite fermions. This is the parton construction. But there's a famous Ioffe-Larkin sum rule that says, if you have a system with fractional excitations, with anions, with partons, then the resistivity add up instead of the conductivity add up. Okay. Now, so the composite fermion itself sees zero effective magnetic field, so it has a very large diagonal conductivity, longitudinal conductivity, right? So which means that the composite fermion resistivity is diagonal, is longitudinal, and small. But the vortices, they actually carry a large transverse conductivity, and that dominates. So what I mean that if you look at the sum of the composite fermion conductivity, it goes as 1/I omega, like an ordinary metal. And the vortex, right, or the flux, this is diagonal, delta mu nu. And this one is basically, E squared over H, epsilon mu nu. It's off diagonal, right? But then one should first convert it to resistivity of the composite fermion. It goes as I omega delta mu nu. But the resistivity of the vortices goes as E squared over H, or H over E squared, epsilon mu nu. So then the resistivity of the whole system is the sum of the two. And you can see this is now dominated by the transverse part, right? So it has a diagonal component, which is I omega. It has an off-diagonal component, which is, let's say, 1/2. Okay, let me set E squared of H to be 0. So then if you convert this into the electrical conductivity, you see now, because at low frequencies, this part dominates over this part. Okay, so once you invert, you get something which is basically proportional to I omega in the diagonal, and the 2 on the off diagonal. So you see that longitudinal conductivity now goes as I omega instead of 1/I omega, right? So that's It's basically coming from the fact that the system is made of the composite fermion and vortices. Yeah. So that's why the Joule weight vanishes. This is a, yeah.
Any other questions? Okay. If not, then let's end on time.